Welcome to the Chapter 1 lecture for Fundamentals of Physics. Before we jump into Chapter 1, which is kinematics and motion, I want to just start with, since this is our first chapter, this is our first real discussion in the physical concepts, I want to start with just a brief discussion on what physics is and why we think that it's important for you to study it. And we always say, and we call this an introductory physics course, and we always say that we're excited and we're happy to introduce you to physics. But there's a little bit of a flaw with that statement, because everyone in their lives has been exposed to physics in some respect. And I don't mean that you've had a physics class before. That's certainly not required for you to have taken physics in high school or maybe in previous college training. We don't expect that. But what you have had is real world, real life experiences. And physics is the science of the real world and explaining how things in the real world actually occur. So anytime you have gone out, witnessed something happening, made an observation, and wondered, how did that occur? Or why did that occur? Then you were acting as a physicist. You were really starting to think like a physicist and study physics. Physicists always want to know why, the underlying reasons why things occur. And then in that, you can start to be able to predict how things will behave and interact with each other. And that is really what physics is. So we start with our basic question. What is physics? Physics is an explanation of how the universe works. It is our best way of being able to describe our observations of the world around us. Now, of course, that does have some limitations because we are humans and we are not perfect. But this is the best way that we understand to explain the interactions between energy and matter and explaining how those interactions occur and why they occur. One of the best ways that we have in order to explain these happenings is using the language of mathematics. We use a lot of equations in this class and corresponding laws that go along with those equations that help us to describe and understand the world around us. So a lot of this course is going to be based on mathematics. It's going to be based on algebra for the most part in this class. And the reason for that is because mathematics gives us the tools that we need in order to describe these real-world observations. Now, in physics, when we solve an equation, we're going to be solving for something physical. We're going to be solving for a unit of distance or a unit of time or some energy or anything along those lines. Whereas in math, maybe before you would solve an equation and then that was it. You just got a number and it didn't mean anything to you. But since physics is the real world, we use math to solve for real world things. Physics is a universal science, meaning that it applies to the largest and smallest objects in our universe, including you. Physics applies to us. Everything that happens on Earth, we can apply physics to. And if we go down to the very, very small level, onto the atomic scale, we can apply our physical laws to that as well. And if we go out to astronomical scales, we can apply those physical laws as well. We can use the same equation to calculate the gravitational force between you and another person standing next to you as you can to calculate the gravitational force between the Earth and the Sun. Even though these objects are obviously much, much different in size, we can still use those physical laws, those physical equations in order to calculate for the smallest and largest objects. So because physics is a universal science, it is a safe assumption that it is also an international science. We have to, as scientists, we need to communicate with other scientists around the world. And most of the world at this point uses the metric system. So in this class, that is what we are going to refer to. Since science needs to use a metric system, that's what we're going to use in this class as well. It is a worldwide science, so that's what we need to use. The English system is based on times when it was the original use of measurement, like when back in the old times when they didn't have a standardized system and they used things that they had around to measure things like their feet or their hands or the distance from their shoulder to the end of their fingers, or paces or anything like that. They got real creative and said, okay, this is how we're going to measure things. But of course, there was a problem with that in that everyone's hands and feet and distance from shoulder to the end of their fingertips is not the same. So it wasn't standardized. Eventually, they did standardize it, usually standardizing sizes and scales to the different body parts of royalty, like kings at that time. But in that, there was not no base units for that system for converting from one value to another. The metric system provides us with that. It modifies base units using prefixes, which we'll talk about some standard base units in just a second. And then the prefixes will tell you whether it's a larger number that you need to multiply by some factor of 10, or it's a smaller number you need to divide by some factor of 10. So it does use base units and also those powers of 10 to more easily relate and more easily and more logically relate these values to one another. So some common base units for this class that we'll use, and I think you will see most of these in this first week. Distance is going to be measured in meters. Mass is going to be measured in grams or kilograms. Mass is a little bit odd in that the standard unit for mass is not going to be the base unit, which is grams, but in this class it's going to be kilograms, which means kilo indicates 1,000. So 1 kilogram would be equal to 1,000 grams. And then time is measured in seconds, force in newtons, energy in joules, and power in watts. And then any of these units can be modified by a prefix to indicate a larger or a smaller value. So if we wanted to say 1,000 meters, you could say 1 kilometer instead of saying 1,000 meters. And of course, 1,000 meters isn't too difficult to write out, but once you get into very, very large scales or very, very small scales, those prefixes really come in handy. All right. So we have two different types of values that we're going to solve for in this class. The first type is going to be a scalar value or a scalar quantity. And this is some quantity that is completely specified by its magnitude. And now its magnitude, I just mean the amount of something that there is. So examples of scalar quantities are mass, length, temperature, energy, or speed. Mass is measured in kilograms, and with that unit, we have a number, and that's your magnitude. So if I say that there's 10 kilograms of mass, then that value is completely fully defined by just saying that there's 10 kilograms. It doesn't need any other information in order to be fully defined. What does need more information is our second kind of quantity, which is called a vector. And a vector is completely specified or fully defined by both its magnitude and then also direction. Direction is the key difference between scalar and vector quantities. Both of them require a magnitude, the amount, the amount of something that there is. But vectors require the direction that that thing is happening in. So examples of this are going to be force, velocity, acceleration, or momentum. Now, when I say direction, it gets a little bit confusing because you think about maybe temperature and you say, well, temperature can go up and down. Is that a direction? But in this case, that's not what we're referring to. When I say direction for vectors, what I really mean is cardinal directions. They can be referred to things as north, east, south, or west, or of course, any combination of those. So we don't say that temperature goes north or south or east or west, but we can say that a force is being applied in the eastward direction. So if a quantity needs to be specified by both the amount of something that there is and then also which cardinal direction it's acting in, then it is considered a vector. And this will be important later in the class because we will have vectors that maybe act in opposite directions and will sometimes cancel each other out or add together. And it's important to know which way those things are acting so you know what to do with those values. All right, so that is the basic introductory information that we need. And now let's jump right into chapter 1, which is patterns of motion and equilibrium. Now, this chapter specifically is going to be rather intuitive to us. We all have everyday words in our everyday vocabulary that we use to describe patterns of motion. We say that objects are slowing down. We say that they're going very fast. We're saying they're going slow. We say an object is turning. All of these words are really good ways that we can use to describe motion, and it's ones that we use in our everyday conversation. So what we're going to do in the lecture today is just talk about these same terms, but maybe in a little bit more of a scientific tense, and talk about the actual vocabulary, the scientific vocabulary behind these things that we already understand. And then we can also apply equations to these. And we'll talk about how to solve these equations and also how to understand these equations, how to read the equations and pull information from them, which is a really useful skill to have this month. If you understand the way to read an equation, to understand the mathematical relationship between variables, you can really understand a lot of physics. So it's a very important skill to have, and we'll walk you through that today. All right, so our first value that we have is velocity. Now, velocity, we might think of it as how fast an object is going. That might be the words that we use if we were just talking in everyday conversation. In physics, the definition of velocity is not much different. It's a measure of distance covered over a change in time. So the equation for this is the one that you see on screen, and it tells you that velocity equals distance divided by time. Now, this probably makes sense to us if we think about it, because anytime we discuss how fast an object is going, specifically a car, we would refer to it in terms of miles per hour, in units of miles per hour. And if we think about this equation, distance divided by time, in the English system, we have distance in miles divided by, which if you change math to everyday words, you could say per, so miles per is distance divided by, and then time, which is how fast it covers that distance. And so it'd be miles per hour. But of course, we're going to be using the metric system in this class, so we're going to measure velocity in meters per second. But it's really the exact same concept, exact same calculation, just with different units. So velocity will be measured in meters per second, distance measured in meters, and t, time, measured in seconds. Now, want to start emphasizing right away, what can this equation tell us? I'm going to tell you a couple of different statements, and they're going to seem very obvious to you because you understand, you've witnessed things moving, you understand speed because we witness speed all the time when we're driving in our cars. But even if I didn't have a real world understanding of speed, of velocity, this equation could tell me a lot of different things just by knowing the mathematical relationships involved in this equation. So what can this equation tell us? The first thing is that velocity depends on distance traveled and the time that it takes to travel that distance. Now, of course, that makes sense to us. We know that that's what velocity and what speed depends on. But if I had no understanding of what speed was in the real world, I could just go to the equation, and whatever other variables are in that equation is what that value depends on. So if I say, what does velocity depend on in some sort of assessment question, then you would just go to the equation sheet and look for the other variables in the equation, and you would see distance and time. So velocity depends on distance and time. What else can I tell? If more distance is covered in the same amount of time, then the velocity will increase. This indicates that you're moving faster. So we know that. If I said to you, if you need to go twice as far in the same amount of time, you need to go faster to do that. And you would look at me and say, well, that's completely obvious. Of course, I don't know why you're telling me that. But we can tell that, again, if we didn't understand anything from the real world about velocity, we could tell that from where these variables are located inside of the equation. And we'll talk more about those relationships, which we call mathematical proportionalities, and I believe on the next slide. So we'll go into that a little bit further. But just understand that this is something that we can just pull from the information that we can just pull from the equation. And then we can also tell that if you cover the same distance in a shorter amount of time, the velocity increases. And again, this is something that we understand. If you get to where you need to be in a shorter amount of time, you needed to go faster to do that. Makes sense. And then finally, a good question to ask whenever you look at an equation is, in what scenario will this value be zero, this value that's solved for? So ask yourself right now, in what scenario just think about it mathematically, will velocity be zero? And in fact, the only way that that can happen is if no distance is covered. So if this value up top, d, is equal to zero, then you end up with 0 over t, and 0 over anything, is just equal to 0. Now, our time isn't going to be 0 because that gives us a little bit of a distance over 0. This actually gives us infinity, but we don't know of any infinitely fast traveling objects, so that's not going to be a reasonable scenario for us. All right. Okay, so let's look at exactly how we can tell what happens to one value when we change another. And in fact, that's a really important skill to be able to develop to understand physics. A lot of physics is all about interactions. What happens to one thing when you change another thing? If you increase one value, what happens to this other value? And we'll be asking you to do that in this class. So this skill of being able to determine that from the equation is going to be very important. So we have 3 different types of mathematical relationships in this class that we're going to talk about. And the first one is when 2 objects are directly proportional to each other. Now, directly proportional means that if one variable increases, then the other variable will also increase. And in fact, they'll increase by the same amount. And in the same breath, you can say if one variable decreases, the other variable will decrease, and they'll decrease by the same amount. Basically, when 2 objects or 2 values are directly proportional to each other, if something happens to one of them, then the same thing will happen to the other. So in our velocity equals distance divided by time equation, we can say that we want to compare velocity and distance. We want to know what happens to the velocity when you change the distance. And since they are directly proportional to each other, as the velocity increases, the distance will also increase. If you decrease the velocity, then the distance will decrease as well. And when we compare 2 values, the third thing in the equation, the time, is going to stay the same. So another way to say this, if you go faster, you cover more distance in the same amount of time. If you go slower, then you cover less distance in the same amount of time. And the directly proportional part tells us that however faster you go, whatever amount you go faster by, the same thing will happen to the distance. So if you double the velocity, then you double your distance in the same amount of time. If you have your velocity, you have your distance in the same amount of time. Now, the way that you can tell this in an equation, it might seem obvious to us because we're familiar with velocities, but the way that you can tell this is by the location of the variable inside of the equation. Now, what do I mean by that? I want to look at if the variable that I'm comparing, the 2 variables that I'm comparing, are they on top of the fraction or in the bottom of the fraction? Are they in the numerator or are they in the denominator? All right, so the first thing that I need to do is check and make sure that the two variables I'm comparing are on opposite sides of the equal sign. You can't compare two values if they're on the same side of the equal sign, so you want to make sure they're on opposite. And in this case, we have velocity and distance, and one's on the left side of the equal sign and one's on the right, so we're fine there. Now, it's obvious with the distance that distance is in the numerator. It's on top of time, so it's on the top of a fraction. It's not quite as obvious on the other side because v is by itself. But I could rewrite this in fraction form. If I was going to write v in fraction form, I would just write v over 1. Anything over 1 is equal to itself. So v over 1 is the same thing as v. And in this case, v is on top, d is on top, and since they're both on top, they're both in the numerator on either side of the equal sign, then they're directly proportional to each other. If they were both in the bottom of the fraction, or if they were both in the denominator on either side of the equal sign, then they would also be directly proportional. It doesn't matter if they're in the top or the bottom, as long as they're both in the same position on either side of the equal sign. All right. Our next proportionality is kind of the opposite of directly proportional. It means inversely proportional. And inversely proportional says that when one value increases, the other value will decrease, and vice versa. And the proportionality part again means that by whatever value one value increases, or by whatever factor one value increases, the other value will decrease by the same factor. So let's look at our velocity equation again. And in this case, velocity and time are going to be inversely proportional to each other. So that means that as the velocity increases, the time will go down when covering the same distance. Another way to say that is if you go faster, it takes less time to cover the same distance. If you go slower, it takes more time to cover the same distance. So remember, whenever we're comparing two values, the third thing or the other things in the equation have to stay constant. So it's always going to be the same distance we're referring to. So the proportionality part tells us that if the velocity increases by a factor of, let's say, 3, then the time will decrease, but it will also decrease by a factor of 3. So if your velocity triples, then your time will be cut by a third. So one goes up by 3, the other goes down by 3. That's the inversely proportional part. And you can tell that from where these things are inside of the equation by, again, looking at where it is in the fraction. Is it on the top or is it on the bottom? And again, I want to put my velocity into fraction form. So I have v over 1, and that equals distance over time. So I compare, the velocity is on top of the fraction, the time is on the bottom of the fraction. Since they're at a diagonal, they are inversely proportional to each other. All right, so let's do an example of a calculation, and I will show you the step-by-step process that I still do every single time that I have a calculation problem in physics. And I recommend that you you do this process for every calculation that you have, and I certainly encourage you to take a pen and paper or a pencil and paper and write this out, physically write this out, because it's a lot easier to do on paper, and it's a lot less likely to make mistakes when you're writing out these calculations. It's hard to do in your head, at least for me. All right, so the first example we have, he says, what is the velocity of a car that travels 150 meters east in 2 seconds? So step 1, define what you know. Write down what you are given in that problem. And usually, if it doesn't say explicitly what you're given in the problem, you're able to tell by the units which values you're given. So in this case, it tells me that a car travels 150 meters. 150 meters is a unit of distance. So I'm going to go ahead and write d equals 150 meters. I would actually physically write this out on a piece of paper if I was doing this problem. And then I see that I'm also given that it does this in 2 seconds. I know that seconds is a unit of time, so I go to my list of things that I know, my known values, and I write t equals 2 seconds. Then I need to figure out what I'm solving for. And then I usually look for the question word in the question, which is what is the velocity? So I know that that's what I'm solving for. So I write v equals question mark. Then step 3 is figure out which equation to use. And this is really the most important part of the battle. After this is just plug and chug, plug in your numbers. Once you figure out what equation to use, then it just becomes straight algebra. So it seems pretty obvious to us right now because we've only had one equation so far in this class. But if we've gone through, week to week and you have a compilation of equations, this process of defining what you know and figuring out what you're solving for gives you a good list of variables to try to figure out which equation you're using. So if you have distance and time and then velocity, those are the 3 letters that you have in this problem, then you go to your equation sheet and you look for a formula that has v, d, and t in it. And of course, this is our first one, so it's right here, located right up top. Velocity equals distance divided by time. Definitely recommend writing out the equation that you're given and then place the values from step 1 into the equation. Just replace the letter with the number that it's equal to. And again, that listing those numbers in the first step really helps you out here. So we replace d with 150 and 2 with the time with 2. And then we just solve. Velocity equals 150 divided by 2, and that gives me a value of 75 meters per second, my final answer. All right, the next step, or the next concept that we have is the concept of acceleration. Now, velocity was the change in distance over time, and acceleration is going to be the change in velocity over time. So if we were talking about acceleration in our everyday lives, we would probably say that something is speeding up. And in fact, it can also mean slowing down, which we'll discuss a little bit more in just a second. But basically, the definition of acceleration is the rate at which velocity changes over time. And the equation that we have here is acceleration equals the final velocity minus the initial velocity divided by the time. So the acceleration is going to be measured in meters per second squared. You can see this is the unit in parentheses down here. Meters per second squared, it's simply the label, simply the unit for acceleration. This square does not mean that you need to square any number in your calculation for acceleration. What this indicates is that you've solved for a change in velocity, which will be measured in meters per second over a second. So it's meters per second, which can be rewritten or shortened by saying, or simplified by saying meters per second squared. So that's where that square comes from. And unless you see a square actually physically in this equation, that's the only time, my circle got a little out of control there. That's the only time that you need to square anything. And if there's no square in the equation, then you don't need to do that. It's just in the unit. All right, so let's look closer at this equation and see what this equation can tell us. First, what does the acceleration depend on? And of course, the acceleration depends on every other variable that's in the equation. So it depends on the change in velocity and also the time that it takes to go from the initial velocity to the final velocity. If the difference between your final and initial velocities increases in the same amount of time, then the acceleration will increase. So this comes down to the proportionality relationship between the change in velocity, which is this whole value right here, and the acceleration. And of course, if I was going to compare these two variables, I would need to put acceleration into my fraction form a over 1 is just equal to a. And so I can see that acceleration and v final minus v initial are both on top on either side of the equal sign. So they're directly proportional to each other. So as the difference between the final and initial velocities increases, then the acceleration will also increase. And then, as you might have guessed already, the opposite is true for the relationship between acceleration and time. Acceleration is in the top of the fraction and time is in the bottom. So if the change in velocity remains the same, but you complete that change in a shorter period of time, your acceleration will increase. If you go from 0 to 60 in 10 seconds, your acceleration is going to be faster if you go from 0 to 60 in 5 seconds. So the faster that acceleration occurs, or the faster that change in velocity occurs, the greater that acceleration is going to be. And now remember the last question, or maybe one of the first, depending on what problem you're looking at, that you want to know is how can acceleration be 0? And in this case, there's two different ways, or one real way. But if there is no change in velocity, then there's no acceleration. And if we think about what are two ways that the acceleration can be 0, we would come up with the fact that if an object is not moving, if it's at rest, if both of these values are equal to, if this one's 0 and this one's 0, you're not moving, then this is going to give you 0 over time, and of course 0 over anything will just be equal to 0. But also, if v final minus v initial are the same as each other, if you're going, let's make this 90 minus 90, then that's also going to give me 0 over time. Remember that you can be going very, very fast. You can be going 90 miles per hour down the highway, but if you're staying at 90 miles per hour, if you've hit your cruise control and you're staying at 90, then there's no acceleration. The acceleration is going to be 0 because there has been no change in velocity, which is the definition of acceleration. So the other way that acceleration can be 0 is if an object is moving at a constant velocity. And that'll be important for us later, so we want to keep that in mind. All right, so we have, because of the way that the equation is set up, v final minus v initial, it is possible to both have a positive acceleration if the final velocity is greater than the initial velocity, meaning that the object is speeding up, but we can also have a negative acceleration if the final velocity is lower than the initial velocity, meaning the object is slowing down. So negative acceleration in physics might be what we refer to in everyday lives as decelerating, slowing down. And then 0 acceleration, as we just stated, means that an object is at rest or moving at a constant velocity. All right, so here's the step-by-step process. I encourage you to do a couple of these practice problems on your own, maybe just change the numbers a little bit. But here's an example of solving for acceleration. An object goes from rest to 50 meters per second in 10 seconds. What acceleration is the object experiencing? And you can see here, I've established my list of what I know right here. My final velocity, where I ended up, was 50 meters per second. It went from rest, so my initial velocity was 0. The amount of time that it took to go from 0 to 50 was 10 seconds, and I want to solve for the acceleration. So I would go to my equation sheet, and I would look for an equation that had VF minus VI, or just had VF, VI, T, and A, and I would find my acceleration equation listed here. So then I simply plug in the values, replace the values from the list into the equation, and I end up with 50 minus 0 divided by 10. That, of course, can be reduced. 50 minus 0 is just 50. And then divided by 10 seconds gives me 5 meters per second squared. You can kind of see where that meters per second squared comes in when you plug in your units into this equation, because you end up with a meters per second, and that gives you a meters per second squared. Now this object was speeding up and the final velocity was greater than the initial velocity, so this acceleration is going to be positive. In our second example, a car traveling at 30 meters per second crashes into a wall and stops in 0.1 seconds. What acceleration is the car experiencing? Here, I'm going to do the exact same thing. I'm going to make my list, but I'm going to be very, very careful of what values I assign to my initial and final velocities. In this case, my final velocity where I end up is 0 meters per second because I've crashed into a wall, unfortunately. So my final velocity is 0. My initial velocity was 30, and all of that change from 30 to 0 happened in 0.1 seconds, very, very quickly. And then I want to solve for my acceleration. So my acceleration, again, same equation, v final minus v initial, but this time I have 0 minus 30, which gives me negative 30 meters per second. And then that divided by 0.1 gives me my final answer of negative 300 meters per second squared. So the negative indicates that this object is slowing down. So it's very important to be careful which values you assign to final and initial velocity, and that just takes careful reading of the problem that you're given. We have a very special acceleration on Earth. This is the acceleration of gravity, and this is the rate at which all objects accelerate towards the surface of the Earth. That number specifically is 9.8 meters per second squared. This is the reason that if you hold a bowling ball and a baseball up over your head, away from your head, and drop them from the same height, that they're going to hit the ground at the same time, because they're both accelerating at a rate of 9.8 meters per second every single second. So if you were thinking about how fast this object is moving, after 1 second, if it starts at 0, then after 1 second, it's traveling at 9.8 meters per second. After another second, it's traveling at another 9.8, it's added another 9.8, so it's traveling at 19.6 meters per second. And then every single second, it's adding on another 9.8 meters per second to its velocity. So that's what 9.8 meters per second squared means. This number is specific to Earth because of the mass of the Earth. If the mass of the Earth was greater, then that number would be higher. If the mass of the Earth was smaller, then that number would be lower. So this number is specific to Earth because of its size. If we went somewhere where the mass was smaller than the Earth, like the moon, then that number drops down, in fact, to about 1.6 meters per second squared. So what that means is that if you drop two objects on the moon, they're going to accelerate at a decreased rate. So that might be why, if you've ever seen videos of the astronauts on the moon, then they kind of walk funny. They're pushing off and they're kind of jumping up in the air. On the moon, you might feel a little bit like a superhero because you could jump a lot higher because gravity's not pulling you down as hard. You could throw a ball a lot further. You could maybe jump off something that you couldn't jump off on Earth and be fine because gravity's not pulling you down quite as fast. But the other end of that is if you went somewhere that's more massive, like Jupiter, pretending that Jupiter was not gaseous and that you could stand on its surface, you would feel much, much heavier on Jupiter. And in fact, if you stood on a scale, it would tell you that you weighed a lot more. Jupiter is 318 times more massive than Earth, so all objects on Jupiter's surface will accelerate at a rate of 24.5 meters per second squared. So you would maybe jump off your desk and hurt yourself because gravity's pulling you down a lot faster. All right, so we say that when we talk about free fall in our everyday lives, this is one of those places where our everyday vocabulary and our everyday conversations kind of gets us mixed up in the study of physics, because we refer to free fall in everyday conversation as any time an object is falling through space, or falling on Earth. If we say someone jumps out of a plane, we'll say that they're in free fall. But the true physics definition of free fall is a little bit different. It has a specific thing that it requires that we don't often refer to. In physics, an object is in free fall only when the only force acting on the falling object is gravity. Most specifically, that means that we're going to be neglecting or considering zero air resistance. Now, of course, that's not going to be an incredibly realistic scenario on Earth because we do have a thick atmosphere, and all objects that fall are going to experience some level of air resistance, some friction acting upward in the opposite direction of the falling object. But free fall is a good estimation for objects that are falling over a short distance and are relatively heavy. If I stand on top of my desk and then jump off of it, air resistance isn't going to have time to slow me down a whole lot. If I jump out of a plane, air resistance will slow me down because I'm falling for a greater period of time. But for relatively short distances and relatively heavy objects, free fall is going to be a good estimation. And free fall is actually a perfect estimation if you go out to somewhere that doesn't have an atmosphere like the moon. If you go to the moon and drop two objects, they're going to fall at a slower rate, but they're not going to be experiencing any air resistance in the opposite direction because there is no atmosphere. So you can search a video online, search for feather and a hammer on the moon, and you'll actually see an astronaut drop a feather and a hammer, and they'll hit the ground at the same time because there's no air resistance that causes the feather to float down like it does on Earth. And like we said, real-world free fall, we have a thick atmosphere, which makes zero to negligible air resistance difficult to obtain, but the free fall equations are good for heavy objects falling over a short distance. Now, this is just kind of a side note, but later in the month, we ask you to do a video project, and we ask you to tell us why it's important for you in your field to understand physics. And one of these, a lot of our degree programs here at Full Sail deal with games or animations or videos or films or anything like that. And it's really important for animations and games to abide by and understand really well the laws of physics. Free fall is one of the ones that you can really tell if you don't follow the laws. You can see that for this falling ball or this bouncing ball, that it needs to accelerate at a constant rate towards the surface of whatever surface it's going to in order to look realistic. If you had that ball and it wasn't accelerating at a constant rate, even if the person watching didn't truly understand physics, because they observed their real world, and physics is the science of the real world, they would look at that and say, something doesn't look right. This doesn't look like what I experience in the real world. So you have to know the rules in order to make believable animations. And then, of course, our animators don't always abide by all the laws of physics. You have guys jumping on buildings and that kind of stuff. But the fundamentals, the basics need to be there in order for the audience to believe what they're seeing on screen. All right, so the equation that we will ask you to solve is for distance in free fall. And the distance in free fall equation allows us to calculate the distance that an object falls when it is in true free fall, meaning that we're neglecting or have negligible air resistance. So the equation is distance equals 1/2 gravity times time squared. So if you look at this, gravity on Earth, and we're going to assume that we're on Earth for most of this class, gravity on Earth is a constant. It's constant. The acceleration of gravity is 9.8 meters per second squared. So that's what this g is. This g is a constant. You're not going to be given that in your calculation, the problem that's listed, because this is something that's a known value. So gravity is 9.8 meters per second squared. And then the time is the only thing that you need to know in order to figure out the distance that an object falls in free fall. So the only thing you need to know to calculate distance in free fall is how long it's been falling. Because gravity is a constant, that's the only other thing in the equation. Now this relationship, if we wanted to look at the relationship between distance and time in free fall, this brings us to our last proportionality relationship, and this is the last of the ones that we'll be exposed to for this month. So we had directly proportional, inversely proportional, and now we have exponentially proportional. And what exponentially proportional means is that in this case, as time increases, distance is also going to increase. They're going to go up together, but unlike the proportionalities that we had before, they're not going to go up and down by the same amount. They're going to have an exponential relationship because of this square on time. So a small increase in time results in an exponentially larger increase in distance. So as time increases by some factor, distance will increase by that same factor squared. So if the time increases by a factor of 2, then the distance is going to increase by a factor of 2 squared, or 4. And the other way as well, if the time decreases by a factor of 2, then the distance will decrease by a factor of 4. They go up and down the same. If one goes up, the other one goes up, but they go up by different amounts by a factor of a square because of that square in the equation. All right, so an example problem for this, an object is dropped and in free fall. How far does the object travel in 3 seconds? We can, anytime you see the words in free fall, that's going to be a good key term to look for the distance in free fall equation. Distance equals 1/2 gravity times time squared. So again, the only thing I need to know is the time. And so the first question there asked me in 3 seconds. It's been falling for 3 seconds. So I plug that into, I plug that into my equation, 1/2 9.8 times 3 squared. Now note that that square only applies to the time. One of the biggest computational errors made when doing this calculation is squaring the entire thing, doing 1/2 times 9.8 times 3, and then square all of that, whatever result you get from that number. But the square in this equation only applies to the time. So what I like to do is I split it up into 2 different steps. I do 1/2 times 9.8, and that gives me 4.9, and then do 3 squared on its own, and that gives me 9 seconds squared. And then my distance is just solve 4.9 times 9, and I end up with 44.1 meters. Now, the second part of the question here, I ask how far does it travel in twice as much time, or 6 seconds? Now I can go through the calculation again. I can do 1/2 times gravity times time squared, and this time plug in 6 instead of 3, and I'll end up with 176.4. But because of the exponential relationship between distance and time, I should already know that if I double the time, if my time increases by a factor of 2, then my distance is going to increase by a factor of 2 squared, or 4. So I could have just taken this first value, 44.1, multiply it times 4, and I end up with 176.4, the same number that if I did it the other way. Now, as we said, this instance of free fall, this explanation of, or the definition of free fall, is not incredibly realistic on Earth because of our thick atmosphere. So we do sometimes have to take air resistance into account. And one of these things where we need to do that is in the case of terminal velocity. Now, terminal velocity, by definition, is when the force of gravity downward is equal to the force of the air resistance upward. So as an object falls, and let's just take the example of a skydiver, and when a skydiver jumps out of a plane, the force of gravity is causing you to accelerate towards the surface of the Earth. As you fall faster and faster, you're hitting more and more air particles. So that force of air resistance is increasing as you fall faster. Eventually, the force of air resistance is going to slow you down enough that the force of air resistance equals the force of gravity, so that the forces actually cancel. You end up with a net force of 0, and you end up not accelerating anymore. And when you're not accelerating, you're still moving because you're still falling, but you're not accelerating, so you're moving at a constant velocity. Remember, constant velocity or not moving can leave you with 0 acceleration. So when you're moving at a constant velocity, because the force of air resistance upward has equaled the force of gravity downward, then that constant velocity that you have reached is called the terminal velocity. All right, and we'll finish up with inertia and forces. And inertia is going to be the property of a material due to its mass to want to keep on doing what it's doing, as referring to motion. So you might have heard this little statement before, that an object in motion stays in motion and an object at rest stays at rest unless it's acted upon by an outside force. That property of materials to want to stay in motion or stay at rest is called inertia. Inertia is an object's natural resistance to change. Now, originally it was thought that an object's natural state of motion was to come to rest. And this was based on real world observations. You watch a ball roll across the ground, you know eventually it's going to stop. But the reason that it stops is not because it wants to come to rest, it's because of an outside force, and that outside force in that case is friction. So the ball coming to a stop is due to an outside force. If you could roll a ball across an entirely frictionless surface, it would roll forever in the same direction and at the same speed, because of its inertia. Inertia is entirely dependent upon mass. The more mass an object has, the more matter that an object consists of, the more inertia it has. And what this means is that it's more difficult to get a more massive object out of its state of motion. So it's more difficult to make a more massive object start moving when it's at rest. And it's also more difficult to make a more massive object stop moving when it's in motion. So I had the silly question here, what is easier to move, an elephant at rest or a bottle of water at rest? And of course, the bottle of water, providing it's not full of some incredibly massive material, is going to be easier to move because it has less mass. All right, forces are going to be a very important concept in this class. Forces are essentially a push or a pull on an object. It's something that changes an object's motion. And this can be causing it to speed up, causing it to slow down, causing it to change directions, which we don't get into a whole lot in this class, but it's basically something that causes an object to change its state of motion. And we'll have quite a few different forces we'll talk about in this class, but today we're going to be referring to mostly applied forces, and these are going to be actual physical pushing and pulling on an object when two objects are actually physically touching each other and having an effect on each other. But we'll also talk about later in this month action at a distance forces. These are going to be things like gravity, electricity, and magnetism that cause changes in motion, but they don't have to be physically touching each other in order to have an effect on each other. So action at a distance forces will be more specific forces that we get into later this month. The equation for force is force equals mass times acceleration. And if you just read this equation the way that it's laid out for you, it really tells you the definition of force. Forces cause masses to accelerate. So force causes a mass to accelerate. It really tells you exactly what it is inside the equation. Forces are going to be measured in newtons. Our mass is going to be in the units we've already recognized, kilograms, and acceleration will be meters per second squared. So one more case today where our everyday vocabulary kind of messes us up in physics. I'm not saying it's wrong, it's just the way that we talk in the real world varies from the true physics definitions. And this is that mass and weight are two different things in physics. We'll say something weighs a certain mass on when we're just talking, and we kind of refer to them as the same thing. But in physics, they're two different values. They're dependent upon each other, but they're not the same thing. Mass is going to be simply the amount of matter that an object contains. It's going to be measured in kilograms. Mass, if you go to a different gravitational environment like the moon or Jupiter or anything like that, your mass will not change. The amount of matter, the amount of particles that you have inside of you will not change. So if your mass is 120 kilograms on Earth, your mass will still be 120 kilograms on the moon. Your weight is what will change. Weight is actually a force. It's just a specific kind of force. And it's a force that you have downward on whatever surface you're standing on because gravity is pulling you down towards that surface. And because it is a force, it's going to be measured in newtons. So your weight will change depending on what gravitational environment you're on. If your weight on Earth is 1,200 newtons, then your weight on the moon might only be 200 newtons. So your weight will change, but your mass will not, because weight is dependent upon gravity. When you stand on a scale, it's actually measuring your weight, not your mass. It's measuring the force upward that needs to support the force that you're providing downward. So it's measuring the equal and opposite force of you pushing downward due to gravity. Pounds, which is what we use to measure our weight, is actually a unit of force, not a unit of mass, which we often mix up. But pounds are a unit of force and depend on gravity. So if you stood on a scale on another planet, it would change because it's measuring your weight and not your mass. So weight is a specific kind of force, and it's this equation here, weight equals mass times gravity, is just another way to write. It's just a specific way of writing force equals mass times acceleration, except for in this case, your force is your weight, and the acceleration is going to be gravity. So W equals m times g is just a specific force, another way of writing F equals ma. So the weight will be in newtons, the mass will be in kilograms, and the acceleration due to gravity will still be in meters per second squared, but this will always be 9.8. And the great thing about weight and mass is that if you know that you're on Earth, then once you know one value, you automatically know the other value, because the only other thing in the equation is gravity, which is the constant. So if your weight is 10 kilograms on Earth, or sorry, your mass is 10 kilograms on Earth, and you want to figure out the weight, all you need to do is multiply times gravity 9.8, and you end up with 98 newtons. If we wanted to know the weight of a 5 kilogram object on Earth, then we would do the same process, 5 times 9.8, and you end up with 49 newtons. You can see that these two values are directly proportional to each other. So if one decreases by a factor of 2, like we have done in this case, we've gone from 10 kilograms to 5 kilograms, then the weight's also going to decrease by a factor of 2. As you can see, we've gone from 98 to 49 newtons. Last concept for the day is net force. Force is a vector, so it is important to indicate which direction these force vectors are going. And we can have parallel vectors, which are acting in the same direction. And in that case, the net force, or the total force, or the combination of all forces that act on an object, will be added together. If they're acting in the same direction, you add those forces together. So in the first example we have here, we have two 5-Newton forces, both acting to the right, and then our net force is just 5 plus 5. Forces acting in opposite directions can work to cancel each other out. So in this case, if we have two equal forces acting in opposite direction, they're going to cancel each other out completely. And the way that we do this is subtracting those values. So we have 5 newtons of force acting to the right, 5 newtons acting to the left, 5 minus 5 is just 0. And in this case, the object is just going to be sitting still. It's going to end up with 0 newtons. It's not going to accelerate. And then lastly, they can either add together, cancel each other out, or they can partially cancel each other out by having one force greater than another force, but they're acting in opposite directions. So here we have 10 newtons acting to the right, 5 newtons to the left. The object is still going to accelerate towards the right in the direction of the 10 newton force, but it's going to be slowed down a little bit by the 5 newtons acting in the opposite direction. So in order to figure out the net force on this object, you subtract the two forces. 10 newtons minus 5 newtons gives you a net force on the object of 5 newtons to the right. Now this equilibrium rule, we say that an object is in equilibrium whenever the net force on the object is equal to 0. So if I go back to that last slide, the middle brick there would be in a state of equilibrium because its net force would be equal to 0. And in fact, this is a very difficult way of saying it. The vector sum of forces acting on a non-accelerating object or system of objects is equal to 0. All that means is that if an object is not accelerating, then the net force on the object has to be equal to 0. And that comes back to our equation that we just learned, force equals mass times acceleration. If we ask the question that I told you is an important question to ask and say, how can force be equal to 0? Well, we're not going to make the mass 0 because if we're referring to an object, by definition, it's going to have some mass. So mass is not going to be 0. So the only way for the force to be 0 is for the acceleration to be 0. So if the acceleration is 0, then the net force on the object also has to be 0. And whenever that is the case, we say that it's in a state of equilibrium. And we have two different types of equilibrium. One where the object is not moving, which is the first way that an object cannot be accelerating. And that is called static equilibrium because the object is sitting still. And then we also have dynamic equilibrium, which is when an object is moving at a constant velocity. So this is our other way that acceleration can be equal to 0. If it's moving at a constant speed or velocity, then we say it's in a state of dynamic equilibrium. All right, that is the end of chapter 1. Thank you all for listening.